on YouTube, keep quiet. But I'm going to try and keep it PG or below. You know, all the dirty jokes that I'd normally say in class, I'm going to sort of tamp that down since these are getting posted on YouTube. I'm just joking. I usually keep it clean. There's not a lot you could say about fluid mechanics, but so the point is me posting these lectures on YouTube, you're able to come back later if there's some concept that doesn't necessarily sink in the first time around. I'll post the link to the lectures in MU Online. Hopefully everybody's used MU Online before, or Blackboard. The grade book is going to be posted there, so that's where you can look to see what your grade is at any point in the semester. It will have the weights built in. So for example, on that syllabus that I've given you, it says that midterm exams are each worth 20%, homework is 15%, and so on. In MU Online, I'll set it up with the weighting for each category so that you can log in and see not only what was your grade on any one individual assignment, but what's your weighted average at any point in the course. And so that same location will have the links to the recorded lectures. Now, I'm not going to take roll. Occasionally I'll have these in-class exercises, and by the way, please write your name on the in-class exercises that we've done today, because I'm going to give you credit for those. That's sort of an informal way of encouraging you to come to class. But you know, if you've got a wedding to go to some Thursday and you're not going to come to class, then just watch the lecture online and get the notes from someone else. Make arrangements to submit the homework to me before you leave. But I'd encourage you to not skip class. I think you'll probably learn better in class than you will out of class, particularly because any problems I solve on the board, you're not going to be able to see that. The recordings, the videos that I'm posting online are recordings of my voice and a screen capture of what's on screen. So if it's an Excel example where I'm typing into the computer, of course that would be visible on the screen recording, but anything I do on the whiteboard won't be. If I have to travel to a conference or something and post the lecture online for that, then I have a different way of editing in examples, but I won't do that in general for all the lectures. Any questions so far? Any questions at all? We've got until 12:15. I find that students are pretty good about reminding me when class time's up. I'll start hearing like zippers. Like, zip, zip. It's like, oh, okay, I guess I better wrap it up. So don't be shy. I'm still getting accustomed to the 75-minute format. Today we're going to be covering fluid properties, and the first few of these problems in the homework assignment that's due on Tuesday, you should be able to solve after today's lecture. So don't wait until Thursday to start on that assignment. Get the earliest start that you can, and even if you get to problem 12 and you realize, oh, I have no idea how to do that one, still read the problem statement, and maybe that will help you to understand the lecture on Thursday a little bit better if you've had a preliminary exposure to the concept. All right, well, let's get into some of the technical material. And like I mentioned before, this semester we're going to be covering both SI units and traditional units, or BG. BG stands for British Gravitational, which is what our traditional unit system is known as. And so there are some things that are relatively straightforward in comparing SI and BG units. And then there are a few places where BG units just don't make any sense at all. Before I came to Marshall, I actually taught engineering outside of the United States. I taught in the United Arab Emirates near Dubai. And the students there, I did the same thing. I taught mostly SI, but some of the problems are in traditional units. And they just thought it was the strangest thing because they didn't have the background of growing up knowing how big an inch is. And they thought, well, why are there 12 inches in a foot? Because they were accustomed to the base 10 system of SI units where there's 10 millimeters in a centimeter, where there's 1,000 liters in a cubic meter. And so the fact that they had to remember that G is 32.2 and some of the unusual conversions seemed a little bit absurd to them. And there are a couple of points in the semester where you'll have trouble keeping track of the BG units. But one of the first things I want to touch on in the case of units of force is the difference between pounds mass and pounds force. And so just to lay the groundwork of that discussion, remember that a Newton, which is a unit of force, is 1 kilogram being accelerated at 1 meter per second squared. In other words, if you have a kilogram of mass and you apply 1 Newton of force to it, then it will accelerate at 1 meter per second squared. Now, the traditional unit of force is a pound of force. And so that small subscript f means a pound force. Now, what a pound force is it's if you had a slug of mass, a slug is the unit of mass in traditional units, and you wanted to accelerate that slug of mass 1 foot per second squared, then 1 pound of force is what you would have to apply. And a slug, by the way, is 32.2 pounds of mass. And that's another one of those conversion factors that's a little bit strange. And maybe the way to remember that is that a pound of force is what you get if you accelerate 32.2 pounds of mass, or in other words, remember that's what we call a slug. So if you accelerate a slug at 1 foot per second squared, that's a pound of force. Or if you had 1 pound of mass and you accelerated it at 32.2 feet per second squared, it would require 1 pound of force. And so what's meaningful about 32.2 foot per second squared? That's g. Yeah, that's gravitational acceleration. And so under Earth's gravity, 1 pound of mass has a force of 1 pound force. And so if I had a pound of candy in my hand, it would be applying a pound of force to my hand, because right now it would be experiencing Earth's gravitational acceleration. There are other accelerations besides gravity. If you have something going around in a circle, centripetal acceleration, like on a ride at the fair, that's a different kind of acceleration than g. If you are in a car and you're speeding up through traffic, that's an acceleration other than g. And so in those cases, a pound of mass wouldn't have a pound of force. It wouldn't be applying a pound of force. And that's when it gets a little confusing, is when you have some gravitational acceleration other than Earth's gravity. So put a little star next to this slide because you'll be coming back to it. There's a couple of problems in Chapter 4 where you'll be scratching your head and you'll be saying, I remember slugs was mentioned the first day of class, and pounds force, pounds mass. This will rear its ugly head a little bit later in the semester. So any questions about this? All right, so just covering units a little bit more. Weight is the effect of acceleration on mass. Weight and force can be thought of as synonymous. And so the weight of an object is the force that's applied under acceleration. We're going to use Kelvin to describe temperature when it comes to the gas laws. Remember that gases like air and compressed oxygen, compressed nitrogen, those gases are fluids, and the ideal gas law, which you probably remember from chemistry, calculations such as those require you to measure temperatures in Kelvin. And it's not degrees Kelvin, it's Kelvin. And in the absolute scale, 0 is the absence of temperature, and 273.16 is where water freezes on the Kelvin scale. Now, anybody know what the corresponding BG unit of absolute temperature is? In SI, it's Kelvin. So if you're thinking in terms of like the analogies they have on the SAT, degrees Fahrenheit goes to degrees Celsius as Kelvin goes to what? What's the BG equivalent compared to the SI? So Celsius and Fahrenheit are both relative measures of temperature. Kelvin is an absolute measure of temperature. Does anybody know what the absolute measure of temperature is in BG units? Very good. Breaking. So it's degrees raking, R. And I don't remember whether you have a homework problem this semester that asks you to do that. Both work and energy are measured with joules, and a joule is the amount of work that's required to apply a newton of force over a meter of distance, and a power is when you apply when you expend work at a certain rate, and so you're expending a certain number of joules per second. There's a temporal component when we start talking about power. So later on in the semester, we won't get back to power until in Chapter 7 towards the end of the semester. But all of those will become important through the study of fluid mechanics. I think that your book has some units conversions among the first few pages, conversions between feet and centimeters, mass, slugs to kilograms, the amount of foot-pounds of force to a newton meter, and so on. There's power versus horsepower. So there we go, raking. Okay, so let's do an example of this. I'd like you to calculate if it was 43 degrees Celsius in Dubai yesterday, what is that in raking? What's the absolute temperature conversion for that? All right, so let's work through that example. Let's take a look. A Celsius degree is bigger than a Fahrenheit degree. So if it is 43 degrees Celsius, then the first thing that we need to do is multiply that by 9/5 in order to convert it to the Fahrenheit degrees, because a 1 degree increase in temperature in Celsius is going to be hotter than a 1 degree increase in temperature in Fahrenheit. And so from that we get 77.4, and then we have to add the 32 degrees, which is the freezing point of water in Fahrenheit, because Celsius has a freezing point of 0. We not only convert for the difference in the degree sizes, but then we also add the 32 degrees. And so that means that it is 109.4 degrees Fahrenheit. All right. And then finally converting it over to raking, it is 460 plus 109.4. So that is 569.4 degrees raking. It's 9/5. So if you look at Fahrenheit is 5/9 of a Celsius. So if you have Celsius and you're converting into Fahrenheit, then you multiply by 9/5. So if we were going the other way, if we were going from Fahrenheit to Celsius, then we'd multiply it by 5/9. That one always throws me for a loop too. And usually I just do it with my calculator. The calculator that I use, it's an HP. It's got a bunch of unit conversions built in, and so I never really look it up. I just always do it in the calculator. That's the lazy way. That's the cheat way. And I highly encourage you to get an HP calculator. They're great. But it seems like most everyone's followed Dr. Pearson's advice and got the Casio calculators, right? That's good. Any questions about this example? Continuing on, we already talked a little bit about this, that mass density is the mass per unit volume. And so in brackets, that's a notation where we have kilograms per cubic meter in brackets. The brackets means has units of. And so occasionally in the notes or in problems, I'll write the units in brackets, and that's just indicating that some variable has units of. Okay, so kilograms per cubic meter. Just as an example, water at 4 degrees Celsius, 1,000 kilograms takes up 1 cubic meter, or the BG equivalent of that is 1.94 slugs, is how many there are in a cubic foot. Why do you think I mentioned the temperature here? Why did I say at 4 degrees Celsius? What's the significance of that? That's when water has its greatest density, right? And so as water cools lower than 4 degrees Celsius, it expands. Or if it gets warmer, it expands. And so if you think about what that means, if the water is expanding, you have the same amount of mass. If I had 1,000 kilograms of water, changing the temperature doesn't change the mass of it. Heating it up doesn't turn it from 1,000 kilograms into 1,002 kilograms. It's changing the volume of space that that mass is occupying. And so you're beyond 4 degrees, up or down from that, the water is taking up more space. The molecules aren't packing as efficiently. And so you're increasing the denominator of mass and unit volume being the denominator. You're increasing that denominator, and so that reduces the density. And so I think there's a table in your book that shows the relationship between density and temperature. In fact, how many of you already have the book? I'm curious. Most everyone's already bought the book. How many people brought it with them today? Let's take a little tour through the book. And can I borrow yours for just a second? Okay, so in the back of the book, there are some appendices that you need to be familiar with. There's an index. That's nice. One of the confusing things, the cheap book is great that it costs less, but there's 2 sets of page numbers. There's the page numbers as it appeared in the original textbook, and that's what the index is based on. And then there's just the sequential page numbers that are, this printing of the book. And they're not off by a lot, but they're off by a little. Okay, so there's the index. There's variable definitions in table A6. The main thing I wanted to show you to begin with, though, is there. All right, table A3. It's on page A8, page 284. On that page, it has the density of water, along with some other fluid properties, at a variety of different temperatures. All right, so it's showing the temperature dependency, and what you can see is that the density is decreasing. Was that air? A8. Okay. Physical properties of water. Table A5. Sorry, next page, everyone. Page 286. There, that's making more sense. I was looking at the density and I was thinking, well, now that can't be right. But this table A5 is for water. The other one was air. So it's showing that water is most dense at the cooler temperatures, and the density decreases as the temperature goes up. Specific weight, as we mentioned earlier, is just the density times G, and so that gives us newtons per cubic meter. And as an example, water is 9810 newtons per cubic meter. In a problem statement, if the problem in the book, or if I tell you a certain temperature, like if I specify 50 degrees Celsius, then what you should do is you should go to the table and find out what are the properties at that temperature. But if no temperature is specifically mentioned, then just by default, the density that you should use is 1,000, or the unit weight that you should use is 9810. Those are sort of like the fallback density and unit weight. Compressibility is another fluid property, and water is generally held to be incompressible. Now, that's mostly true. It's just a lot less compressible than air. Air is very easily compressed in comparison to water. Water will only compress a little bit. But even though we generally hold that water is approximately incompressibility, that doesn't necessarily mean that its density is always constant, because if you add salt to water, then its density increases. There's more mass in the same amount of volume for seawater than there is for fresh water. And specific gravity is a fluid property that relates either the density or the unit weight of a fluid relative to the density or the unit weight of water. And just as an example, mercury is a fluid that comes up in a lot of the problems that we work, and the specific gravity of mercury is 13.56. And so, for example, if we wanted to know what is the density of mercury, what we would say is it is the density of water times the specific gravity. And so the density of water is 1,000 kilograms per cubic meter, and the specific gravity is 13.56. And so therefore 13,560 kilograms per cubic meter is the density of mercury. And so that's how you use the principle of specific gravity. It's a ratio of something's density to the ratio of water's density. So just as an example on the other end of the spectrum from mercury, which is very dense, oil will generally, since we know that oils are less dense than water, they float on top of water, you might expect that the specific gravity of oil is going to be less than 1. And so that's why it floats, is because it'll have a density of less than water. All right, just a reminder that if the temperature is given in a problem statement, look it up out of the table, and if it's not, then those are the default values that you can assume. Okay, well, that's all we're going to do for today. Remember this day because it's going to be one of the rare lectures in the semester where you'll get out early. But it being the first day of class and all, I think that the extra 16 minutes is just my way of saying welcome back to the semester. I've got office hours from 12:30 until 2, and then remember we've got lab starting at 2 o'clock today. And so we're going to be meeting over in the lab by all the fluid mechanics equipment. We're going to be talking about some safety issues, the required report format. So does anybody have any questions before we finish for now? Yes. Yes, I do. I want those. I want to grade them and give you credit for them. All right, so I'll see you at 2 o'clock.